In this video series, we are going to be going over the course notes for the precise definition of the limit. Within this course, on any assignment you may have that isn't the bonus assignments, any quiz, midterm, or final, this will not be covered. However, there is a bonus assignment just focusing on the precise definition of the limit at a point. That bonus assignment is worth 2% of your final grade. First, let's discuss the precise definition of a limit at a point. So we let f of x be defined for all x not equal to a within an open interval of I, such that a is in that open interval I, and let L be a real number, then the limit as x approaches a of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Well, let's break this down a little bit, okay? So the first thing we're going to do is we're going to break it down graphically, and we're going to break it down into the three pieces, okay? F of x is defined for all x equals a within an open interval I, such that a is in I. And we're going to look at three different graphs. We're going to look at the graph here, where we have a hole at 1, everywhere else y equals x plus 1. So this could be the function x squared minus 1 over x minus 1. Right? Then we have the following graph. Where our knowledge from limits tells us we have a jump discontinuity. But we're going to explore this in terms of this first point. Then we have the graph that looks like this. Okay. And we're just going to analyze our first part of the definition. It's defined for all x not equal to a within an open interval I, such that a is in I. And we're going to look at a equaling 1. So if we look at the x value 1, here, if I create just an open circle around 1, this line is defined everywhere except for at 1. Here, as once again, I create that open interval, it's defined everywhere except for at 1. Now, for our last example, it doesn't matter how small I make my interval, there will always be parts of this interval that don't equal to a that are also not defined. Because of this jump or this gap, the limit would not exist. So our first condition being that f of x has to be defined for x not equal to a within an open interval I, such that a is within that open interval I. Here, we satisfy the definition. We satisfy the definition. We do not satisfy the definition. So here, our second example, we could simply state the limit does not exist. So for in these or looking at these examples, our first two conditions satisfy the beginning of the statement. Okay. So let this be true. Well, it's true for the first two, but it's not true for the third. And the order in which we express this statement matters. Okay. So let's look at the next part. Okay. The next part is let a be a real number, then f of x, the limit as x approaches a of f of x equals L, if for all epsilon there exists a delta greater than 0. For all epsilon greater than 0, there exists a delta greater than 0 such that If 0 is less than the absolute of x minus a is less than delta, then the absolute of f of x minus L is less than epsilon. This is an if-then statement. If-then statements are as followed. If A, then B means that if A is true, then B must also be true. The way that this statement is given here can be kind of confusing because we have a then if when it's really an if-then statement. So the parts of the expression, we have two parts. We have the then the limit as x approaches a of f of x equals L, and we have this if. But really, our A statement, our if statement, is this blue statement here. Is for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute of x minus a, which is less than delta, then the absolute of f of x minus L is less than epsilon. While the B statement is the limit as x approaches a of f of x equals L. That means that if we prove that if for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute of x minus a, which is less than delta, then f of x is minus L is less than epsilon. We have shown that the limit exists. So what does this statement mean, and how do we prove it? There are four main parts to this statement, and the statement that we are referring to is our statement A. Okay. This statement A has four main parts, and the order in which they appear is super important. So let's break this statement down a little bit before we try and start solving problems. So the statement is if for all epsilon there exists a delta such that if 0 is less than x minus a less than delta, then f of x minus L is less than epsilon. So the order of the statements is really important. So for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute of x minus a, which is less than delta, then f of x minus L is less than epsilon. Here, this symbol here is an epsilon, or here epsilon and delta are two positive numbers. Okay. In this situation, you pick epsilon first. You can pick any value, but once you have picked it, it's fixed. So the first thing you do is you pick an epsilon and you fix it. Whatever you say epsilon is, it's now that value. You don't give it any numerical value, but it's simply a fixed epsilon greater than 0. One way to think of it is you can create this number line where you have, oh, that was not so great. If you take a number line and you let this be 0, here is epsilon, there's going to be a little bit of a gap. Right? No matter what epsilon you pick, there's going to be a little gap. Not a big gap, but a little gap. Okay. Now, based on the epsilon you picked, so once you've picked that epsilon, based on that epsilon, a delta must exist. So once that epsilon has been picked, now the delta, we determine whether or not the delta exists. Such that if x minus a is between 0 and, or the absolute of x minus a is between 0 and delta, then the absolute of f of x minus L is less than epsilon. In almost every situation, almost every time, what we're going to do is we're going to let delta be some function of epsilon. We don't have an exact value for delta. It's simply Well, given your epsilon, here's a function which determines a valid delta. And we prove that given that delta that's built using epsilon, then our f of x minus L is less than epsilon. Now, before we discuss this algebraically, let's discuss it geometrically, okay? So here in our first example, we have this nice graph, which to make it a little bit nicer, I'm going to make this a nice big circle. Let's pretend this circle is open. Now, if we draw dotted lines going up here, okay, and I take this section of the curve, okay, every point except for A, every point except for A, we lie within f of x we lie within this band here. So if I let this be L, this be L plus epsilon, this be L minus epsilon, my curve lies within this error region, this plus or minus epsilon. So we would say the limit existed. And remember, we pick this band, this plus or minus epsilon first, then you can pick a delta based on this epsilon. But if we look at the function, and we look at the function with a quarter epsilon here, okay? If we let L be 2, then while it does work coming from the right, coming from the left does not work. Or sorry, well, it comes from the left, it works. Coming from the right does not work. If epsilon equals 1/2, then L equals 2 does not work. What about L equaling 1? Well, if I once again do a quarter, about 1, well, now the limit from the right does work, but the limit from the left doesn't work, okay? And if I let L equal 3/2, well, that's here, and neither limit works. And in fact, no L works. There is no L such that if we have an epsilon, then there exists a delta greater than 0 for epsilon equaling 1/4. Okay? So because of this, the limit doesn't exist. Since epsilon is picked, if we can define delta using epsilon to satisfy our condition, then we have shown that the limit exists. All this is to say, to show the limit exists, we need to pick a function g such that if 0 is less than the absolute of x minus a, which is less than g of epsilon, then f of x minus L is less than epsilon. Okay, so our focus is going to figure out what this g of epsilon is to make this condition satisfied.